we'll have 4 solid days of practice next week, so we should be all feeling fine about this stuff. All right. N1 and N2, they kind of overlap quite a bit, so all the notes are together. N1 is more concept building, making sure that you understand what a definite integral is and explain how to estimate its value. And then some of the connection stuff between integrals and limits and derivatives and integrals. The 4 stuff we're not going to talk about today because we're just laying the groundwork, so that stuff we'll probably cover on Monday. And then N2 is actually the estimating part. Now, along with derivatives, when we talk about integrals, there is a way to find the exact value of an integral, but we're not going to get into that until later. So this is more just laying the groundwork for what an integral is and how to estimate it, much like we did with the derivative. You lay the groundwork for the derivative, what it is, and how to estimate it. And then later on we'll get into how to find the exact values. Alright, so last standard we estimated the derivative of a function, which is the instantaneous rate of change of y with respect to x. The other way that you can think about this is that it's the slope of the curve at a particular x. Because when you talk about rate of change of y with respect to x, remember that with respect tells you what's your dependent and what's your independent. So y is dependent on x. In this standard, we will learn about one type of integral, the definite integral. We haven't even really talked about that yet, so we'll kind of learn through this example. Suppose you're driving your car. The velocity increases for a while and then levels off. Now, when I say velocity of a car, if you had to give me units for the velocity, what would you say? Miles per hour. Velocity in this case means speed. So if you say miles per hour, is that value usually positive or negative? Positive. Now, why is it important to say velocity here and not speed? What's the difference between the two? Direction. Yeah, velocity indicates speed and direction. So if it's a positive value, that means you're moving forward, right? So technically, if we're going to be technical here, if we were moving backwards, the velocity would be considered negative because you're decreasing in the direction you're going. Alright, so the velocity increases for a while, then levels off. We're going to draw a sketch of the graph showing the velocity increasing from 0, then approaching and leveling off at 60 feet per second. So let's start with writing or drawing our axes and labeling them appropriately. What is my x-axis going to be represented by? Time. It's some time value, right? It's probably seconds here. Oh, I haven't told you what they are yet. But yes, this is time, and it is going to be in seconds. And then what is my y-axis? Careful. What's increasing for a while? What does it say increases for a while? Velocity. What are the units for velocity here? Feet per second. So the velocity is what increasing, so that is actually my unit here. So you could write velocity in feet per second. So your y values here represent velocity, not distance, but velocity. Okay, let's mark off some values here. We're going to go for 100 seconds, and then I want you to mark off 10 tick marks. So I went halfway for 50, and then 10, 20, 30, 40, 50, 60, 70, 80, 90. And then mark 30 and 70. Because in our picture here, I haven't given you all the information, but when we draw the graph, there's certain things that are going to happen at 30 and at 70. Where are we supposed to be leveling off, though? What's my velocity we're supposed to be leveling off at? 60. So draw 6 tick marks up. 10, 20, 30, 40, 50, 60. Okay. And then we'll sketch a rough picture here of what's going on. All right, it's going to start leveling off at around 30 seconds. So between 0 seconds and 30 seconds, if we start from standstill, what is my graph going to look like? Is it going to be a line? Why is it not going to be a line? Yeah, can you start from 0? Can you start going 30 feet per second, like right away? No, you have to gear up to it, right? So you can't just automatically go from 0 to nothing. I mean, you have to have some time there to increase speed. So you're not going to have a straight line, but it is going to be a sharp increase, but there should be a little curvature to it. So we're going to increase quickly until about 30, and you're going to start to see this start to level off. So this is like you're increasing in speed up until the speed limit, which hopefully here is 60 miles per hour, not like 25 miles per hour. Okay, and then it starts leveling off. So how can I show that the speed has leveled off? A little plateau. Now, it technically probably isn't a straight line, but in our graph, our sketch, we can kind of show it as a straight line to get the idea that we are leveling off our speed here. Okay. You have two regions of area here underneath the curve. One where the velocity is changing and one where the velocity is constant. What section has velocity that's changing? About this section right here, because the velocity is increasing that whole time. And then at about 30, it looks like my velocity is constant. Okay, so I have two regions of area. We're going to go ahead and split that up using a dashed line. And we're going to stop at 100 here. Okay. Describe these parts of the graph. So if I wanted to describe this part of the area, I would say that velocity is changing how? Somebody said it. Yeah, it's changing quickly. We could say increasing quickly, or this is fine too. Velocity is changing quickly from 0 to 30 seconds. The velocity starts to level off at 30 seconds and stays that way. And at some point, the car would run out of gas, so it would have to stop going 60 miles per hour. So we couldn't say that forever, but for the part of the graph we're looking at, it stays the same. All right. Now, how can we find distance traveled using this graph? There is a formula that you've used probably in science classes. I know we've used it in Algebra 1 and Algebra 2. It's a very simple formula, but it has everything to do with distance, rate, and time. So I'm going to give you an easy beginning question here. If I said your speed, on average, was 60 miles per hour, and then I asked you, how far did you travel in an hour, what would you say? 60, okay. And then if I said, okay, you're still traveling 60 miles per hour, but how far did you travel in 2 hours then? 120. What are you doing with the speed and the time? Doubling. You are multiplying them. So if you wanted to find out how far you went in 3 hours, you would take 60 and multiply it by 3. So 60 miles per hour is your rate. The hours that I want you to figure out how far you went is your time. You are multiplying rate and time to get distance. I don't know if you've ever noticed this up here. This used to be an equal sign, then I had a student way back when who changed the equal sign to an I. Alright, so how can we find the distance traveled using this graph? You can find the distance by multiplying what two things? Rate and time. Distance equals rate times time. That's a very common formula that we use naturally when we're talking about car speed and distance traveled, but applies to any time you have a rate and a time. Okay, so with a graph, we can estimate the distance by finding the areas under the curve. Now, if the problem, and this is a very common application, because actually what we're talking about here is an integral. This is a very common application of integrals in Calc AB, because this is like the beginning of calculus, where you are finding distance. Now, in order to find distance from the function by finding areas underneath the curve, the y-axis must be what? It wants to be positive, but it must be a rate, right? You can't find distance by multiplying rate and time together if your y-axis isn't a rate. If it's something else, it's not going to necessarily work. So as long as the y-axis, that wasn't good English here. As long as the axis, I don't even know how to fix that. There we go. I was copying out what I wrote last year, but then I realized, yeah, that didn't make sense last year either. Alright, the y-axis must be a rate value. And then what must the x-axis be? The x-axis must be time. If those don't match up, then you can't find distance using area underneath the curve. Okay, so let's actually approximate before we flip the page here. Let's go ahead and approximate what these areas are. So if I wanted to approximate the area of this shape, we said that's closest to a rectangle. And if I want to multiply rate and time together, I'm really multiplying y values and x values. So what's this distance approximately? 60, right? And then what's this distance? 70. So 60 times 70 would be 420, right? And is that miles, feet, centimeters? It's in feet. So this is approximately 420 feet. That's what that area represents, is that you've traveled 420 feet because you've multiplied rate and times together. 4,200. Oh, yeah, because they're both, sorry. Yeah, they're both in the tens. Good. 60 times 70. And then, in this section here, if we were doing a triangle, because that's probably the closest shape right now that we have to that, is it going to be an overestimate or underestimate? It's going to be an underestimate, but that's okay. My x here is 30. My height here, because I'm trying to find the area of this, is still 60, but with a triangle, the area formula is 1/2 base times height. So base is 30 times height, which is 60, so 60 times 30 is 1,800, and then divide that in 2, you get 900, right? And so that's 900 feet. So total, you've gone about what? 5,100 feet. So approximately 5,100 feet. Okay. math example to start with. Go ahead and flip. The process of evaluating a product in which one factor varies is called finding a definite integral. Now, let's go ahead and identify what some of these words mean. What does product mean? Multiply. Usually you're looking at just, in this case, in this class, you'll just be multiplying two things together. So there'll be an independent, which is your x, and you'll have a factor that varies, which is always your y. So in this case, what was our factor that varied? Did time vary? Velocity varies. So one factor varies. Usually this factor is my y. But multiplying two things together where one of them varies, so multiplying x and y together in a function, is called finding a definite integral. You can evaluate definite integrals by finding the corresponding area. There are several methods we use to approximate definite integrals. There are more exact methods coming up, but right now we're just estimating. So let's get a good definition down first that we can keep referring to. Okay, the product of two factors, and when I say factors, I mean like two things that you're comparing in the problem or that are associated in the problem. So like an x and a y. So the product of two factors where one factor varies. And then we're going to include some of the things that integrals are used for. Okay, integrals in calculus find distance and total amount of something. The other way that I say this too is accumulation of value. Such as you have a function and your x value is time and your y value is your stock value, your stock price. Stocks go up and down and vary over time. If you want to find the total amount that you've made in 10 years, you would use a definite integral and find the area underneath the curve to figure out how much accumulation of value you have over that time. So these are the two main applications, and really, I mean, in Calc AB, which is what we're doing right now, that's all you would need integrals for, those two things. Which is nice because they're easy to recognize when those two things are in play in a problem. Okay, methods to estimating definite integrals. When given a graph, you're going to approximate the area under the curve. Now, I say area underneath the curve, knowing that sometimes it's not going to be a curve, it might be a line. But it's just under the graph, you're approximating the area underneath the curve. We haven't done this yet in a problem, but we will in example 1. So we do this by counting boxes. We do this by using geometric formulas. I mean like the area of the triangle that we used on the previous page, find the area of the rectangle. Those are geometric formulas. We'll just stick with those two because we haven't talked about the third one yet. And then when you're given a function, we usually have to graph the function. There's not really another way to estimate the integral value. We graph and follow method number 1. or use a rule we have not talked about yet. This is what you're learning over the weekend. So, or use the trapezoidal rule. Because the trapezoidal rule we can actually put into our calculator. We have to know how to do it by hand, but we also put it in our calculator. And if you have a function, that's when you would use the calculator. Alright, so let's look at example 1 here. I thought I drew graphs on here. Oh, I have them over here. I'm going to have you skip to example 2. We'll do these two, and then if we need another one, we'll go back to example 1, but I didn't have a grid there, so it's going to make this a little more difficult if you don't have a grid. Okay, let's start with evaluate the definite integral of this function f of x equals 8 times 0.7 to the x from x equals 1 to x equals 7. Okay. Now you will get used to knowing what this means, but when you are asked to evaluate the definite integral, what that is saying is multiply x and y. Because remember, the definite integral is the product of two factors where one varies. My y is the thing that's varying here. Now, when you say multiply x and y, this is finding the area. Okay. Now comes the fun part. Go ahead and graph it on your calculator and get a good screen, if you would. Does anybody have a good window? Well, really, if we stuck with maybe just a regular window, so from -10 to 10. You don't see much of it, so we have to zoom in a little bit. Okay, so we only want to go through 1 to 7, right? Okay, what do you notice about my graph? And this is something you're going to have to do, because for what we have to do with the calculator, you need to have like your graph filling up your whole screen. Is my graph filling up my whole screen right now? No. And when we find, I should say this, when we find area underneath the curve in this problem, we're looking at positive area only. So my graph doesn't even look like it comes below the x-axis. I'm going to stick with this area right here between 1 and 7. So I'm probably going to play with my window a little bit here. And on my x-min, I'm going to go 1. My x-max, I'm going to go 7. So it only has the x-values that I'm looking between. And then let's see what happens there. Okay, so I'm getting a little bit better. Can I change my y-axis to even make it nicer? How do I do that? Or what should I do for that? Minimum 0. Okay, it's even a little bit better. Maybe I can go down to 7 or 6. Let's go down to 6 or 7, sorry. Okay. This should give me a pretty good graph. When you're estimating definite integrals, you want to make sure that on your calculator you have as much of the graph as you can filling up your screen. The other thing that you need to make sure is in play with your calculator. If you go to the zoom button, you see how it says format above it? Hit second and zoom. You need to turn your grid on. go back to your graph, you'll see that all these little boxes up here. Okay. This is how we estimate the area underneath the curve. Now, it's gonna be hard to see the screen. Well, I'm gonna have to do some of it on the side here. Well, actually, I'll just do it on my calculator. Okay. So when I'm estimating area here, I only want what's underneath this curve. And we first have to identify what each one of these units are worth. So for this box here, have I changed my scale so this is worth more than 1? No. Hit your window button. You see where it says X scale, SCL, and Y scale? If that's 1 and 1, that means the area of each one of these boxes is 1 by 1. Right? So if I said, what's the area of this? You would say 1. Now there will be times where you're going to have to adjust those scales to make your screen fit nicely. You just need to make sure that if you change those scales, so maybe the X is worth 2, that you then know the area of your box is 2 times 1 instead of just 1. Okay? That is something that we're going to add here. Okay. First thing I do on my little sheet here is I identify that each box that I'm going to be using to estimate is worth 1. So I draw my scale that I used on my calculator. And then I look at my graph, and I'm going to go through and count how many whole boxes are underneath radicals. So let me identify here. Like, here's one box. Is that whole box underneath the curve? No. Is this whole box underneath the curve? Yeah. Okay. So I'm counting up all the boxes that are totally underneath the curve. Yes, sir.
What if it touches the line, but it's still...
Like, are you talking about this one?
No, the one...
This one?
No, right.
This one?
Yes.
I would count that as a whole one. Yeah. Okay, so we're going to go ahead and... Oh, I don't have a... Let's see. Okay, that works. I have 1, I have 2, I have 3, I have 4, I have 5, 6, 7, 8. Would you count this one? 9. Would you count this one? I mean, it's close enough that I'm okay if you count it. Okay. So what is that, 10? Okay. So we have 10 whole ones. And now comes the fun part of estimating the rest. Okay, so we're going to start up here and work our way through. And you're going to have to help me here. Approximately how much area, if this whole thing is worth 1, approximately how much area is right there? Like that the little tiny one right there. Like 0.1, 0.2. It's going to be pretty small, right? Okay. So maybe you say it's 0.2. So I'm going to write 0.2 there. 0.2 of that square. This one, somebody said approximately half. Would everybody agree with that? Yeah. About half. So maybe you say, okay, 0.5. What about right there? About 0.3, is that what you said? Okay, so 0.3. And then this one, 0.9. Oh, you can't even see it. Sorry. This one right here. Maybe 0.9 because it's really close to being the whole thing. Okay. Right here. Sorry. I forget I zoomed in. Right here. Whoops. Like 0.3. Okay. Now, what am I doing by saying 0.2, 0.3, point whatever? I'm estimating. Is everybody's estimate going to be exactly the same? No, but should we be pretty close? Yeah. Okay. Um, this one's going to be about 0.5, probably. And then I have this one and a little part right there. So maybe I add 0.1, and then what would you say this last one is? 0.7? Okay. So I'm going to add 0.1 and 0.7. Now, the scale here is worth 1. So, like, finding the area of all these little parts is easy. But let's say the scale it wasn't a 1 by 1 square. Like the next one we're going to do is not a 1 by 1 square. What you're doing is you're multiplying each one of your approximations by your scale. So here, it'd be the same as if we added up all my decimals, but sometimes it's not, so I like to show the work anyway. Alright, and then we take our calculator, after I wipe mine off. Okay. And you add up 10. Oh, my batteries are low. Okay. Are you guys adding them up for me? 13.5? Okay. So last year, some of our decimals were a little bit different, but we got 13.6. So okay. So the definite integral is 13.5, and because this represents the area underneath the curve, I'm going to write unit squared here. But that's my answer. That's the value of the definite integral. And then in your graph here, I want you to just draw a sketch of what your graph will look like. And then we're going to shade in the area that we found. So from 1 to 7, didn't our curve kind of come down like this? My graph turned off. It was like an exponential decay, right? So it doesn't have to be like totally perfect, but for what you see on your screen, you should show it there. The other thing that I want you to show is, like if you went from 1 to 7, I want you to show that on the x-axis to show me what your window was. And then what was our window on our y-axis? 0 to 7. Okay. All this does, like on a test, if you're estimating, is show me what you were looking at when you graphed it. And then if something's off, I can go back and I can check with the same window. Yeah, sorry. This is the area that we found. Okay. We're going to do something pretty similar here, but with a different function. We'll see if we're doing okay. Okay, so example 3, we're going to estimate the definite integral again. Okay, so our new function is a quadratic. It's a quadratic that opens down. And we're looking between the time values of 0.1 and 1. So your first task is to do what with that function? Put in your calculator and graph it. So I want you to get a good window, or attempt to figure out what that window is going to be. 14. This is a clue to know kind of where to go with your window, this span that they're looking at. So we're looking between 0.1 and 1. Now, this is the graph that I have initially. Does anybody have a good window? Sophie?
I did my X min 0.1 and my X max 1, and then I did my Y max 35.
35.
My Y minimum.
0. Okay. Now, for these, can we assume, we haven't done 4-type problems yet, but for right now, we can assume that your Y min can be 0, because when we look at area underneath the curve, we're looking at positive area. Because normally if you're talking about area, does it make sense to talk about negative area? Technically, no. If you're talking about an area of a room, it's going to be a positive value. So, notice here, because my X min and X max are weird values, like from 0.1 to 1, to make it a nice graph and spread it out a little bit, I change my X scale. This would be an appropriate time to change your X scale, and I change it to 0.1. What does that do for me if I change it to 0.1? It makes hashes at every 0.1. So every hash mark that I have then moving forward is 0.1 in my graph. So if this is your window, when you go to hit graph, I get a very nice spread out graph. If you don't change your hash marks, it's going to make your graph really, really squished. And so this spreads it out a little bit. It's the same graph, it's just a different window to look at it in. This is a very good graph to work with. Before we actually change over the grid, let's go ahead and sketch this. We went from 0 to 35, and then from 0.1 to 1. And then I just want a picture of it. So, again, it doesn't have to be perfect. But approximately. Huh? Yep. And then I'm finding just the area underneath the curve, so just lightly shade, because that's what we'll be finding. Okay. I'll come look at it. Oh. My grid's being funny. Are other people's grids like that?
Yeah.
Okay.
Are you gonna have to do the Y scale though?
I think we have to change our Y scale too.
I don't think we did.
The reason we have to change my Y scale too is because my Y scale is still by 1s. So that makes...
It's too big.
Yeah, it makes it too big. So we need to go back to the Y scale, and I'm going to change my Y scale now to 5, because the disparity between the two scales is too big. So if you change your Y scale to 5, now I'm back to like nice grid marks. Okay. So if you have a funny grid when you go to graph, then just play with your scales a little bit until you get to a place where you have some nice spots to show you. Did you fix it? Yeah. Okay. So that is why at the very beginning I draw my scale box here. The Y was a value of 5, and what was my X? 0.1. So 5 times 0.1 is 0.5. Like if I find the area of each of a single box, that area would be 0.5. That's going to be important when we get to this part where we're multiplying everything by the area that it represents. Okay? So I want you and a partner. Does everybody feel okay with like doing the counting up boxes and approximating? Okay. I want you to pair up with somebody. You two can go. I want you to pair up with somebody, and I want you to work together to approximate the area, and then we're going to check people's answers and see how close they are. Okay? This will take you about 5 minutes, probably.
One question.
I thought you just shake usually.
What? Just practically your face looks weird. Whatever. 1, 2, 1, 2, 3, 4, 10. 10 at the bottom. 9.
original seats